Well, good morning, guys. I'm glad to see you here. I guess I should give a few minutes for other folks to show up. So we'll go ahead and outline what we're going to do today. Okay. So today, we're going to get more practice with IBP. I'm going to show you what are called looping integrals. I'm going to show you some new integration by parts stuff. So we'll get practice with the problems that are similar to the ones we looked at on Wednesday, but also we'll learn this new IBP technique. And then if there's time, I'm going to introduce next week's material, which is section 7.2 on trig integrals. So this is the plan. How are we doing? Are folks getting in? Getting there. I kind of feel like I should wait just a few more minutes because we're still kind of slim. But in this time, if you could take a second and go ahead and type into chat just the numbers of a few problems from the homework that you would like to see. So we're going to begin with some practice problems. Numbers 9 and 13, don't stress about. Those are both looping integrals. We don't know how to do those yet, but I'm going to be showing you those to you today. So if there are any homework problems that you guys would like to look at, go ahead and type those problem numbers in chat. Again, the numbers that I wouldn't type in there are number 9, this guy, because we don't know how to do him yet, and also number 13. Those two are part of a family of looping integrals that I'll be showing you today. I guess I should leave this open. Okay. And while those are coming in, I'll just remind everybody the tool we've been using, which is integration by parts. Which you'll see me abbreviate as IBP because it takes too long to write. And this just says if U and V are both functions of X or functions of some other variable, then the integral of U dV is equal to U times V minus the integral of V du. Or if it's a definite integral, the integral from a to b of u dv, that's u times v evaluated from a to b minus the integral from a to b of v times du. So I want to remind you, of course, the definite version, you have to evaluate the u times v piece between bounds also. I know I keep saying that, and I don't want to be a broken record, but you'd be amazed how often I see people forget it on tests, and it hurts you. So please remember that this is how the theorem works. I see we've got lots of problems requested, 2, 5, 14, and 10. So 2, 5, 8, 10, 14. Let me take a look at those. 2, 5, 8, 10, 14. 14 I'd certainly be happy to do. 2, 5, 8, 10, let's see, 5. Yeah, 2, 5, 8. Okay, we'll do a few of these. I'll start with 2. 2 is approachable. It's not at all hard. But if you haven't been exposed to this, then it might seem a little bit intimidating. I think it's a good way to start our Friday morning here. So this is going to come from homework 3, number 2, and then I probably won't do all of those, but I'll do a few of those. So in mine, and your numbers might be a little bit different because WebAssign changes the numbers at random. I'm told to evaluate this integral. If I wanted to differentiate this, I would definitely use the product rule. So integration by parts is a reasonable attack for integrating it because it's a backwards product rule. Another way to think of it here, you've got a polynomial times a trig function. And you may remember from Wednesday's lecture that anytime you have a polynomial function times sine, cosine, e to the x, that's always IBP, always done by parts, and it's always done the same way. So we follow our Lipet rule. Remember how this works. If you have any logs in your integral, you should choose that for u and everything else for dv. If you don't have any logs, but you do have some inverse functions, then you should choose that for u and everything else to be dv. If you have neither of those, but you do have a polynomial, then you should choose that for u and everything else to be dv, and so on here, with the last two being exponential and trig. So in this problem, I do not have any logs, I do not have any inverse functions, but I do have a polynomial. 9x is a polynomial. It's a polynomial with one term, but it's still a polynomial. So according to my Lipet rule, I should choose that to be u. And then everything else is dv, so cos 4x dx. I need to complete my IBP table. That means I need to find du and v, which are calculated from u and dv. If u is 9x, then du is 9 dx. And if dv is the cosine of 4x, this is a little micro u sub. So if that was just cos x, then v would be sine x. But it's not, it's cos 4x. So this is going to be sine 4x, but then you have to divide by 4. From the chain rule. So this would be sine 4x over 4. And if you want to go off to the side and do the substitution to pass from dv to v, that's okay. But remember what we've been saying, our goal is to get to a place where we can do these little micro u sub problems kind of in our head. Any questions about why the IBP table looks the way it does? The sun's starting to come in here. Let's fix that. So if we're all comfy with how we chose u and dv, and then we're all comfy with how we calculated du and v from those, then we can go ahead and plug into the formula. This is an indefinite integral of u times dv. So it will be equal to uv minus the indefinite integral of v du. That's 9x times sine 4x over 4. Minus the integral of sine 4x over 4 times 9 dx. And generally what you want to do after running IBP, that's what we did here, we ran IBP, you want to ask whether the integral that it spits out is easier than the integral you started with. Is this easier than the integral I started with? If yes, why? If no, why not? Anybody? Have things gotten better or worse? Better, yeah. Why? Because the polynomial's gone, right? This is now just sine 4x times a constant. There's no x outside to contend with, so I can go ahead and integrate this. Yeah, exactly. Brian's got it. So let's take care of these constants. 9x times sine 4x over 4, that's 9/4 x sine 4x. And here I can also pop a 9/4 out of the integral, and I'm just left with sine 4x dx. Sorry, I started to write secant there. That's sine. And the integral of sine 4x is not hard. This is another micro u sub. The integral of sine x is negative cos x. So the integral of sine 4x is going to be negative cos 4x over 4. And at this stage, we would start writing our plus c because I have no more integrals. And this bit we can clean up a little. The 2 minuses will make a plus. The 4 times 4 downstairs is a 16. So this is 9/4 x sine 4x minus 9/16. Sorry, plus 9/16 cos 4x plus c. Hey, Bubba, how you doing? You're looking mighty handsome there, Hamlet. Yes, you are. So good boy. Okay, so questions on this guy. This is a good warm-up problem. Not too bad, right? Not too bad. All the work really is in choosing u and dv and then completing this table. There's 2 little micro u subs, and remember we do want to get to the place where we can do those in our head. So the integral of like sine ax or cos ax, we should be able to do those quickly in our head, the same way we can do like the integral of e to the ax in our head. It's okay to write them out. But have in your mind, you start looking for patterns, right? There is a pattern there with all of those micro u sub integrals that is very easy to spot. And you can save yourself a lot of time in writing by spotting and using those patterns. So the next one that we wanted to look at, 5, 8, 10, and 14. I don't think we have time to do all of them. Happy to do 5. 8, we can look at 10, 14. Let's do 5 and 14. And maybe we can look at one of those other guys. But there is some new material today. So number 5 here. Asks you to integrate the natural log of the square root of x dx. And there's more than one way to think of this. Depending on how comfy you are with log rules, you can trivialize this problem pretty quickly. So first, does anybody see any smart algebra that we could do before getting started on the calculus? Hammy, be good. Be good, baby. Yeah! Yeah, remember the square root of x is x to the 1/2. And then rules for logarithms, this power can come down front. So this is the same as the integral of 1/2 ln x dx. So that's the same as 1/2 integral ln x. And we did the integral of ln x last week, or not last week, Wednesday, last time we met. This is a straightforward by parts problem. I won't run back through it here, because I want to go and then solve this integral another way. But you remember from Wednesday's video that if you solve this integral by parts, you get x ln x minus x, and then slap on your plus c. All right. So this is one way to attack this. This is the fast way for sure. But what if you don't notice that? Okay, this is the fast way, and the path from here to here is integration by parts, right? Here you would run IBP with u equal to ln x and dv equal to dx. We did that in class last time, so I don't want to run back through that right now. Check out the video from Wednesday to see that done. But if you didn't notice that you could rewrite this like this, then you have to do something else. And that something else is a little bit more complicated, but I think it's good practice. So let's pretend like we didn't know that rule for logarithms. I would run IBP, and here I do have a log. I look at my Lipet rule to choose u. I do have the ln of the square root of x. That is a log function, so I would pick that to be u. And that means dv would have to be everything else. That's just dx. du then, this is going to require the chain rule. Do we remember how to differentiate log functions like this? You get 1 over the inside, and then you have to multiply by the derivative of the inside. That is 1/2 x to the negative 1/2. And v would just be x. Now this du, if you simplify this, and you should, you've got 1 over root x, that is x to the negative 1/2. And so this and this can play together. You get 1 over 2x dx. This is 1 over root x. This is 1 over root x. 1 over root x times 1 over root x is just 1 over x. And then the 1/2 gives us the 2 downstairs. So from here, we would say the integral of natural log square root x is u times v. That's ln square root x times x minus the integral of v times du. So this is, I'll write the x out front because it just looks prettier, x times ln root x. Minus here, the x's cancel, so you just get 1/2 integral dx. And the integral of dx is x. So this is x times the natural log of the square root of x minus 1/2 x plus c. And you might ask, is this the same as this? The answer is yes. If you were to use that log rule to rewrite this square root x in here as a 1/2 power and pull down the 1/2, then this becomes this. So either attack is fine, but I hope you'll see why this first approach is so much more slick. You get the algebra out of the way at the start, then the integral is trivial. I mean, it wasn't trivial before Wednesday because you didn't know how to integrate the natural log before Wednesday, but on Wednesday you did learn how to do this. And so your mind should be doing this all the time. Anytime you can reduce a problem to a problem you've previously solved, mathematicians love that shit because then it's done. You don't have to do anything. There's this great joke about an engineer, a statistician, and a mathematician dealing with a fire. And each one comes up with their own way of dealing with it. And the mathematician, I think, brings the fire to the engineer and says, I've reduced it to a problem that had previously been solved because the engineer had already put out his own fire. So that was a stupid little joke, but It exemplifies the spirit of the mathematician. So either one is fine. Questions on either of these approaches for number 5? That's good. If I can get a little rise out of you on a Friday morning, I'm happy with that. The actual joke, feel free to Google it. There's a whole universe of jokes out there. The scientist, the engineer, the mathematician, and the something else, usually statistician. Where did I get the x on the -1/2? So I integrated dx here. So from this line to this line, all I did is evaluate, I solved this integral. So the integral of dx is x. So 1/2 integral dx is 1/2 x. The 1/2 came from this 1/2 here. So you cancel these x's and you just have 1/2 left. Then I pop it out and integrate dx to x. Cool. Any other questions on this one? Okay, we managed to do that pretty quickly, so I think we got time to come back and look at 1 or 2 others. That was 5. We also wanted 8 and 10. 8 takes a little while, but I'll go ahead and show you guys. I don't see any real harm in that. We did one like this on Wednesday, where I think we integrated like x squared e to the x. So this is z cubed e to the z. I'm going to ignore the 21. This is 10. 8. So when I integrate z cubed e to the z dz, whatever constant is there, you just pop it out. Here my integrand is a polynomial z cubed times an exponential e to the z. So I'll run IBP. And according to my Lipet rule, do I have any logarithms? Nope. Do I have any inverse functions? Nah. Do I have any polynomials? Yeah, z cubed, that's a polynomial. Okay, so that's going to be u, and everything else will be dv. So then I take differentials. du is 3z squared dz. And I integrate here to get v is e to the z. And one run of IBP here looks like this. I'll have u times v, so my original integral is equal to z cubed e to the z minus the integral of v du. So I'll write the polynomial piece first again because it looks better. 3z squared and then e to the z dz. A word to the wise, cross your z's. Otherwise, they look like 2's. You can pop out the 3. And what you notice is that this integral is actually similar to the integral you started with. Z cubed e to the z, z squared e to the z. The net effect of running integration by parts once, you spit out this chunk and you reduce the power of the polynomial by 1. It still has the overall same shape, polynomial times exponential. So the way to solve this integral is more IBP. So I'll call this IBP1. This next guy I'll call IBP2. Again, I choose u to be the polynomial piece, which is z squared, and dv to be everything else, which is e to the z dz. du will be 2z dz, and v is e to the z. And now I will replace this integral by his IBP equivalent. So the z cubed e to the z out front, he just coming along for the ride now. Then you have minus 3, and then you need to open a big paren, because this 3 belongs to this integral, this whole integral. And this whole integral is about to be replaced by a difference of 2 objects. So that 3 would need to be distributed to both. So anytime you replace an integral by its IBP piece, always do so with a big paren out front. Now here, this integral is equal to u times v, that's z squared, e to the z, minus the integral of v du, that's 2z e to the z dz. And again, I'm writing the polynomial piece first just because it looks good. Now I'm going to distribute and sort out all my negatives. One of the things you're going to find again and again as you solve these integration by parts problems is that you'll have like a negative that needs to be distributed and a negative here, and you have to be careful with your parentheses and your minus signs. There's lots of places where they can get jumbled up, and you'll see several other examples of that today. But I just want to emphasize the importance of these big parens and that you are careful with your algebra. So let's clean up all the constants, distribute everything, combine whatever we can, you know. So this is z cubed e to the z minus 3z squared e to the z plus 6 integral z e to the z dz, where the 2 and the 3 make 6 and the minus make plus. And what you notice again is that this sumbitch still the same shape as the original, still polynomial times exponential. So the same attack we used here and here, we should use here, because this integral looks just like this integral, looks just like the original integral. They're all polynomial times exponential. The nice thing here is that with one more run of IBP, you notice every time I run IBP, the power of z comes down. Z cubed here, z squared here, z to the 1 here. So with one more run of integration by parts, I will have no more polynomial and I'll be able to finish the problem. So my third run of IBP is going to look like this. U will be the polynomial piece, which is just z, and dv will be everything else, which is e to the z dz. du now is just dz, and v is e to the z. So this will be my final run of IBP for this problem. And the output will look like z cubed e to the z minus 3z squared e to the z plus 6, open big paren, u times v, minus the integral of v du. Like that. And now one last time I need to distribute, make sure I'm being good with my minus signs, and the integral that's left over is easy. So this is z cubed e to the z minus 3z squared e to the z plus 6z e to the z minus 6 integral e to the z dz. And finally, after 3 runs of IBP, we get out an integral that doesn't have any polynomial, that is just an exponential. So we can evaluate that integral directly. The integral of e to the z is just e to the z. So overall, our answer is z cubed e to the z minus 3z squared e to the z plus 6z e to the z minus 6 e to the z. And you slap on your plus c now because there are no more integral symbols. There are some patterns to recognize here. First, most obvious, the power of z, the degree of the polynomial piece here was 3. And it took 3 runs of integration by parts to solve the problem. This is true in general. If you have a polynomial of degree n multiplying an exponential or sine or cosine, those will all be done the same way. You'll run integration by parts n times. Every time you run IBP, the degree of the polynomial will go down by 1, and eventually he'll be gone. And you can just integrate whatever, the sine, the cosine, the exponential. There are fast ways to do this. Imagine I stacked these 3 tables on top of each other. I could just calculate a sequence of derivatives, z cubed, 3z squared, 6z, and 6. And over here, I just stack the antiderivatives. They're all just e to the z. You look at the final answer down here, you notice a pattern, right? Z cubed e to the z minus the derivative of z cubed times e to the z plus the derivative of 3z squared times e to the z minus the derivative of 6z times e to the z. So this and this and this and this is a sequence of derivatives, whereas this, 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 and this is a sequence of antiderivatives. The trick that will allow you to do this quickly is not a part of the official Santa Fe curriculum. If you have a polynomial times sine or cosine or exponential, you can use what's called tabular integration by parts, where instead of having those 3 IBP tables separate and going through this long process, you kind of build all 3 IBP tables at once and then just write down the answer. It's pretty cool shit. It can save you a lot of time. I'm not supposed to teach it to you, but you know, Google, right? Tabular IBP is good stuff. It's not useful for anything other than these, but these show up a lot. Having a polynomial times sine, cos, or exponential function shows up all the goddamn time. So it's useful to be able to do them quickly, and the pattern here is not hard to see. You could probably come up with this on your own. So I do think it would be worth your time to Google tabular integration by parts if you are interested in that sort of thing. You can always do these problems like I've just shown you. And how I've just shown you is the official way I'm supposed to teach you. So, you know, it's good, it works. But it's a little time consuming, right? It's not, you know, it's kind of boring. There's no creative steps here. There's nothing really hard. It's just like turning a crank, and you keep turning it and turning it and turning it until the polynomial goes away. So this trick is a nice trick, and I encourage anybody who's interested to Google it and employ it. You're free to use tabular IBP on exams if you like, and on the homework, of course. But there's no pressure to do so. I'll never demand that you use tabular IBP. And if you are feeling a little bit lost or overwhelmed or something like that, I do not recommend doing that. Stick to what you need. You don't need tabular IBP. But if you're feeling a little bit bored and a little bit underwhelmed, then by all means, check it out. Questions on this problem? I'll do one more example problem like these from the homework, and then I'm going to show you the new method, which is not really a new method, but it's a specific thing you can do with some by parts problems. So what else did we want? We wanted 10 and 14. Let's do 10. 14 isn't hard. If you're having a hard time on 14 after you set it up, I think the integral there should look like 2 pi x e to the x minus e to the negative x. Split it up into 2 different integrals. But 10 here is a good problem. 14 is a fine problem too. And if you want to see it, come by office hours. I'll be happy to do that with you guys in office hours today. But 10 is a nice definite integral. We haven't gotten a lot of practice with those by parts. It's the integral from 1 to 7 of w squared times the natural log of w. And the natural log is a special function. It's like a, you know, sine, cosine, e to the x. It's a transcendental function, but it doesn't have the same sort of derivative behavior as sine, cosine, or exponential functions, which all kind of differentiate to one of the others. So here again, we are definitely going to use integration by parts, but we're not going to differentiate this piece until it goes away. We're going to do something else. And this is where your LIPET rule will help remind you of the strategy. I do have a logarithm function here, so I should really pick this to be u and this to be dv. So following that LIPET rule will get you out of a lot of sticky situations. This is one of them. So according to LIPET, I should pick u to be the natural log of w, and then dv to be everything else. That means du is 1 over w dw, and v is the integral of w squared is 1/3 w cubed. That's funny, these are all kind of the same shape symbol, aren't they? The 3 is like a sideways w. Anyway, okay. So here's my IBP table for this problem. The difference between this and the previous is that this is a definite integral. So I have to remember to evaluate everything. And you should do the evaluation right away. For the u times v piece, don't wait till the end. If you wait till the end, your hand will get sore from writing shit you didn't need to write. So here's u times v. I'll write the polynomial piece out front again just because it looks better. 1/3 w cubed times the natural log of w, evaluated between bounds, between 1 and 7, minus the integral of v times du. That's 1, so integral from 1 to 7, 1/3 w cubed times 1 over w dw. I'm going to do two things in the next step. I'm going to clean this up. I can pop out the 1/3 and then w cubed times 1 over w, it's w squared. I'm also going to evaluate this. If I plug in the lower bound of 1, then I'll have 1/3 times the natural log of 1. Natural log of 1 is 0, so lower bound contributes nothing. Upper bound gives me 7 cubed over 3 times the natural log of 7. And like we said, when I plug in the 1, I get nothing. I get 0. So then I'll have minus this integral. So that's minus 1/3 integral 1 to 7 w squared dw. 7 cubed is 49 times 7. It's too early and I'm too lazy. Let's just leave it as 7 cubed. That's fine. The integral of w squared dw is 1/3 w cubed. So this is 7 cubed over 3 times the natural log of 7 minus the 1/3, and the 1/3 from the integral will give me 1/9 w cubed evaluated from 1 to 7. So at the end of the day here, I have 7 cubed over 3 times the natural log of 7 minus 1/9 times 7 cubed minus 1 cubed, or 7 cubed minus 1. And that's it. And you know, if you have a calculator or if you want to take your time to do the arithmetic here, you're welcome to do it, but I don't care. I guess it's 343, right? 343 over 3 times the natural log of 7 minus 1/9 times 342, if you want to. Okay. Questions on this guy? It's a nice, cute little problem. This is about the caliber of an exam problem, okay, if you're curious. If exam 1 has a straightforward IBP problem that's not intended to be tricky or test any special skills besides IBP, it would look something like this. One run of IBP, as long as you do everything right, the answer falls out very quickly. Okay. I'm going to change gears. I want to make sure there aren't any questions on this or the previous example, or Are we sure we're all comfortable with those? Is there anything anybody would like to ask? Because if not, we're changing gear for a second. Maybe while you gestate, I'll get some water. Oh. I'll be done with this class in about 40 minutes. My second cup. I've got about an hour break after I finish this class. We'll knock it out. All right. Totally encourage you to do that, Sergio. Great idea. Start a group me, start a Discord, talk to each other. Do it. Do it, do it, do it. Talk to each other about this math all the damn time. Just don't do it on tests. I'll figure it out if you do. Don't do that shit. But talk to each other about these problems. It'll help. Okay, so if there aren't specific questions about any of the examples that we've done, then I am gonna change to talk for a little bit about doors. Has anybody heard of a dash pot? Or has anybody ever tried to slam the door at a convenience store or something similar, large retail establishment? Even on campus, I think, at most of our doors on campus. If you try to slam the door, it won't slam because there's this little thing up on the top there. It's a little box with a little hinged arm coming off of it. Inside that hinged box is a little gas piston, a little gas cylinder with a piston that moves back and forth in it. And that dampens the action on the door. It keeps the door from accelerating in one direction or another too quickly so that it can't be slammed. That object is called a dash pot. The system I'm about to draw is called a damped harmonic oscillator. You take an object and you put it on a little cart. That object has a mass m. And over here you have a wall. And you attach to that wall a spring. One side of the spring is fixed to the wall. The other side of the spring is fixed to your little cart. And if you were to pull this guy out and let him go, then he would bounce back and forth. Can everybody imagine that? That's called a harmonic oscillator. And I always forget whether there's 1 or 2 L's in oscillator. If you look at something moving in a circle, straight on from the side, it also looks like this. It just appears to go back and forth. That is also a harmonic oscillator. So these show up in nature in a lot of different places. The system, the physical system I'm giving you here is kind of the simplest physical system that will give you that behavior. Okay, remember the dash pot. If I place a dash pot over here, and I attach that to my mass also, then the system is going to do something interesting. It'll still want to go back and forth. The spring and mass system still wants to oscillate. But this dash pot is going to do what dash pots do. It's going to dampen that motion. It's going to soften the acceleration. So can you imagine what would happen if I pulled this guy over here, I pulled my mass on wheels over here and I let it go. The spring's still going to pull it back, but it's not going to pull it back super fast or all the way to equilibrium. It'll pull past equilibrium, but not all the way to the other side because the dash pot's going and slowing it down. And it'll continue to oscillate back and forth, but it'll oscillate less and less and less and less and less because this dash pot has a dampening effect on the motion. So this is called a damped harmonic oscillator. Yeah, think of the dash pot as like a car shock. Exactly. Not the springs, but the shocks itself. So you've got like a shock over here attached to your harmonic oscillator, the thing that wants to bounce back and forth. And that shock is is absorbing some of the energy of the system, making this thing bounce less and less each time. Kind of like a pendulum that swings less and less and less and less and less each time. Same sort of behavior. Or if you had a satellite orbiting something and the gravity here was strong enough to pull it in, if you look just from the side, that orbit is going to look like this as it comes in, right? It starts out here, it's orbiting, it's orbiting, it's orbiting, but the orbit gets smaller and smaller and smaller until it crashes. So all sorts of places where damped harmonic oscillation occurs. This is the simple physical system used to describe damped harmonic oscillators, and without the dash pot, just harmonic oscillators, in MAP 2302 differential equations. So it's sort of the simplest physical system that will give you that behavior. And this is called a spring mass dash pot system. But the behavior that you get out is damped harmonic oscillation. Harmonic oscillation is just the term for like sine or cosine wave, right? Just what the cart would do if you didn't have the dash pot. And then the dampening is like having a function that goes to 0 times sine or cosine. Because they show up in physics so many different places, because they show up in nature in so many different places, the behavior of the system is something that we care about, and we want to be able to work with all the functions involved. The equation of motion for a system like this, and it depends on what kind of dash pot you have there, would be like e to the minus t times cos t. The cos t just wants to wobble back and forth. The e to the minus t is coming from the dash pot, is slowing down the wobble. I'll show you what the graph of that function looks like. Looks like this. So you've got your cosine wave, but you see the waves are getting smaller and smaller and smaller and smaller. So the regular cosine wave, that's your harmonic oscillator, and then the damped harmonic oscillator just makes the waves get smaller and smaller and smaller. So if you wanted to figure out how much distance this thing covered, this little cart, how far it rolls back and forth over that whole process before it stops bouncing at all, you would need to integrate this. And this should look kind of familiar. This kind of looks like number 9 in your homework. The trick for integrating something like this I'm not a physicist. I just care about the mathematics. And I know that evaluating this integral is crucial to understanding physical systems like this well. So as your math teacher, I would like to give you that tool. So can we evaluate this? Well, you'll find every time I ask a question like that, the answer is going to be yeah. We use IBP, but this integral is special. We call them looping integrals. So the reason I'm taking so long to build this up is because looping integrals are a little bit weird. When I teach this stuff in person, I can watch the brains of my students slowly drip out their ears. We call them looping integrals because we're going to do IBP. We're actually going to use IBP twice for this guy. And then the original integral is going to show back up as the output from IBP. That will allow us to then solve an equation for the integral without actually evaluating the integral. It's very sneaky. Sorry, I've got something in my eye here. It's driving me nuts. So looping integrals, these are problems where after some work, the original integral shows up again, shows back up. allowing us to solve an equation, an algebra equation for the value of the integral. All right, so that's what looping integrals are. The most famous one is called the damped harmonic oscillator. The most general way of writing that, or the most common way of writing that, is something like this. But you could have like e to the minus 10t times cos 5t, or e to the minus 0.1t times cos pi t, anything like that. When you integrate things like that, they will always be looping integrals. Looping integrals we solve with integration by parts, and then some clever algebra. MIT has a great video on spring mass dashpot systems if you're curious about where these come from, or other systems that behave like this. Search MIT Arthur Matic for the differential equations video from MIT. You'll have to sift through a few of them. They have all of them up there, but it'll be one of the early ones. Okay, so let's do it. I want to evaluate we'll do this one. We'll do e to the minus t times cos t. But again, it could be e to the minus 5t times cos 2t. You could put any constants in there you wanted. We're going to use IBP. And I'll follow my Lipet rule. So no logs, no inverse functions, no polynomials, but I do have an exponential. So I'll pick that to be u. And I'll pick dv to be everything else. So then du, the derivative of e to the minus t, is minus e to the minus t dt. And v, the integral of cos t, is sine t. And I'll call this IBP1 because I know I'm going to run IBP twice. According to integration by parts, my integral is equal to u times v minus the integral of v times du, which I will write as minus e to the minus t times sine t dt. I can pop this minus out and make that a plus. And notice that the integral I'm left with is the same sort of shape as the integral I started with. The integral I have to do now is e to the minus t sine t. The integral I had to do at the start was e to the minus t cos t. The only thing that's changed is the cosine became a sine. So whatever attack I used for this would also be appropriate to use for this. In other words, I'm going to run IBP again. I have to choose u and dv the same way, so u will still be e to the minus t. It'll be my exponential part following Lipet. And dv now will be everything else, that's sine t dt. du is minus e to the minus t dt. And v now is minus cos t. I have the e to the negative t sine t out front, coming along for the ride, plus, now I'm going to replace this integral by his IBP equivalent, and I always like to put that in parentheses, even if there isn't something there, just to remind myself that that's an important habit. U times V, that's negative e to the negative t cos t minus the integral of V times du. Well, here this is negative and this is negative, so that will be positive e to the negative t cos t dt. And the magic, believe it or not, has already happened. We don't need to do any more calculus. All the calculus is done. I'm going to take what I have here and rewrite it in a single line. Right now what I have is that this integral is equal to this stuff. Okay, so let me rewrite that as a single line. My cat is snoring and it's adorable. Sorry if you see me looking over there and smiling awkwardly, that's why. So what do we have? I've got e to the negative t sine t minus e to the negative t cos t and then minus the integral of e to the negative t cos t dt. This might look kind of intimidating, but it's really not. Imagine I gave this thing a name. I call it I for integral. Then what this line says is that I is equal to e to the negative t sine t minus e to the negative t cos t minus I. You can solve this equation for I just using algebra. Add I to both sides. I know it looks like someone's work from 1033. On the left-hand side, you have 2I. On the right-hand side, you have now just e to the minus t sine t minus e to the minus t cos t. So I is that over 2. In other words, the integral of e to the negative t cos t is equal to this. And you tack on your plus c. This business where you label the integral as I, you don't have to do that. You could just add this to both sides. If you add this to both sides, you'll get 2 times this integral equals this stuff. So the integral has to be that stuff divided by 2. Personally, I don't usually write it like this. Usually I would just add this integral to both sides. So I'll show you how that would look. Personally, from here, I would say, and if you wanted to copy that down, just leave space, hang out for a minute, don't panic. Personally, from here, the way I write it, I just say 2 integral e to the negative t cos t dt has to be this, e to the negative t sine t minus e to the negative t cos t. And then I divide both sides by 2. And tack on the plus c. Right, this is what my usual workflow for this problem looks like. But I think folks usually have a little bit of a hard time seeing what we're doing. I'm just adding this over to the other side. Since this is the same as my original integral, I've got like, you know, an apple plus an apple is 2 apples. But that step of abstractifying or abstracting by labeling the thing as I and then adding it over, for some reason, some people really like that. So I'm not going to tell you one way or the other is better. Either one is fine. Here we just label this as I. And you see that the things are the same. Okay, give me a thumbs up react if this is making any sense. Let me get a feel for how we're doing with this. I know it might seem silly, but since I can't see your faces, I need to know. It's okay if it's not. Okay. Okay. So let me see how I'm doing for time. I've got 2 other things I wanted to show you, 2 other examples I wanted to show you here today. Another one is another looping integral. So when it comes to number 9 in the homework, this is what you need to do. Right? You need to do this. You need to run integration by parts twice. And then what you'll see is your original integral shows up. He comes back. That's why we call it looping. I have posted some resources for you here in Canvas. Take a look at these. Come to modules. Scroll down to the section on integration by parts resources, and you'll see a handful of nice things. Stack Exchange post kind of explaining how IBP works, what it is, the proof. Paul's online notes, really good. Really, really good written explanations and written examples. And then these Patrick JMT videos, these first 3 are like what we've been doing for the most part, Wednesday and the first few problems today. But this last one down here, this is another example of a looping video, another example of a looping integral. So take a look at that for more practice. I'm going to do one more looping integral for you here today. And this is a good introduction to where we're going. So where are we going? I'll continue it here. Okay, so next week is all about trig. So if you don't like trig, take a bravery pill, you know, whatever it is that you need. Specifically, section 7.2 is on trig integrals. These are like integral of sine squared x times cos to the 4x, powers of sine times power of cosine, and stuff like secant cubed x tan squared x, powers of secant and tangent. And the other section we're going to cover next week is 7.3 on trig sub. So that'll be doing integrals like 1 over the square root of 2 minus x squared dx by subbing something like x equals the square root of 2 times sine theta. Both of which are going to require a lot of fluidity with trig. In particular, you need to know your trig identities. The critical identities for next week sine squared plus cos squared equals 1. Tan squared plus 1 equals secant squared. There is a third version of this so-called Pythagorean identity which is 1 plus cotangent squared equals cosecant squared, but we won't use him as much. The others that we'll be using a lot, there's a double angle identity, sine 2 theta equals 2 sine theta cos theta. And this identity you actually need to do number 14 on homework 3. So just a little note there. The other identities like this are going to be so-called half angle identities. Sine squared theta equals 1/2 1 minus cos 2 theta. And cos squared theta equals 1/2 1 plus cos 2 theta. So these identities you are absolutely going to need next week. And the last looping integral that I wanted to solve for you today is actually a trig integral. So it's a really good introduction to section 7.2. I want to solve for our last problem today the integral of secant cubed x dx. In addition to these identities, there's one other thing that we need. We will need to remember a particular problem from section 5.5, the integral of just good old-fashioned secant. Does anybody remember the integral of good old-fashioned secant? It's a weird one. We did this in section 5.5 in the first week, but the way you do it is a little bit strange. It's a u sub, but first you have to do something wonky. You multiply by secant plus tangent over secant plus tangent, and then you substitute for the denominator. This turns out to be the natural log of secant x plus tangent x, of course, plus c. So this is one of your fundamental antiderivatives. It's in the chart in table, or it's in the table in section 4.9 and also in 5.3. And it's one of the antiderivatives we should know. I will cook it up again fresh for you next week. But in case you're not remembering, tangent's natural log secant. It's in here somewhere. That doesn't matter. It's one of our fundamental integrals. And I'll remind you where this comes from next week. But for now, I want to attack the secant cube problem. And for that, we're going to need this. We're going to need this and this identity. All of these identities, though, we're going to use next week, and we're going to use them freely, like fast. I'm not going to be taking time to cook them up or remind you where everything comes from. So make sure these get baked into your noodle real good. All right, let's do our last example for the day. We're going to integrate secant cubed, and it's a looping integral. Most of the trig integrals we're going to be doing in section 7.2 will be easy. They'll just be some combination of trig identities and u sub. But some of them, if you're trying to integrate an odd power of secant times an even power of tangent, some of them will require integration by parts. And this is the fundamental example of one of those. So the time to do it is now. I want to run IBP on this, so I could pick u to be secant cubed and dv to just be dx. If I followed LIPET, that's what I would do. But LIPET doesn't really help me here. Instead, because if I integrate the dx, I'm going to get an x, and that's going to mean the integral that I do that I get as the output would be worse. It would still have like secants and tangents and shit, but then it would also just have a few x's floating around. Fuck that noise. So instead, we're going to split it like this. Secant times secant squared. I'm going to pick this to be dv because it's easy to integrate secant squared. And I'm going to pick this to be u. This looping integral only requires one run of integration by parts. That's nice. And it's not hard. Du, the derivative of secant, not the antiderivative, but the derivative of secant, that's secant tangent. So of course, when we get to 7.2 next week, you're not only going to need your trig identities, you're going to have to remember all the derivatives of trig functions also. V, the integral of secant squared, is just tangent. So here's my little IVP table. I'll continue the problem down here. According to the integration by parts formula, the integral of secant times secant squared, which is secant cubed, is secant tangent minus the integral of tangent times secant tangent. So let's write that down. That's secant x tangent x minus the integral of, if I multiply these two, I'll have secant times tangent, or secant times tangent squared. Looking just like this. Here's where I use my trig identity. I know that tan squared x plus 1 is secant squared x. So if I subtract 1 from both sides, tan squared x is the same as secant squared x minus 1. So this tangent squared, I will replace by parentheses secant squared x minus 1. So I'll have secant x times secant squared x minus 1. So far, just one run of IVP and use of this identity. That gets me to here. Now I'm going to distribute this secant. So I have minus the integral of secant cubed x minus secant x. That's what I get when I distribute my secant. And now I'll distribute the minus out front here and split up the integral, right? Because I've got an integral of this minus that. So this is, gotta be careful with your negatives, secant x tangent x minus the integral of secant cubed and then minus minus makes plus the integral of secant. And the integral of secant, I told you that's something we're going to need for this problem. It was a 5.5 thing, but so I'll leave the minus secant cubed integral. But this piece is the natural log of secant x plus tangent x. No, I'm not going to write the plus c yet because I still have this integral here. Does everybody see why this is a looping integral? Here's my original integral showing up again. I have looped. Remember what all this is equal to. All this is equal to the integral of secant cubed. So let me write that in a single line. Integral secant cubed x dx equals, I'm going to put these two pieces out front and then minus this. So I'll have secant x tangent x plus the natural log of secant x plus tangent x minus the integral of secant cubed x dx.
Professor,
Yes.
where'd you get the natural log of secant plus tangent x?
So that is the integral of secant.
Oh, that is okay.
Yeah, so remember, this is one of the kind of things that we needed to remember from previous sections. So this is a u sub problem. I'll go back through the derivation of that integral. It's not too hard, but it's a u sub problem with some sneaky algebra. But for now, for the purpose of this problem, because I'm just trying to teach you looping integrals, I'll ask you to, if you don't remember this, trust me or Google it or whatever. But yeah, this natural log of secant plus tangent is the integral of secant from this line. So what I end up with is the integral of secant cubed equals secant tangent plus natural log secant plus tangent minus the integral of secant cubed. So I'm going to add the integral of secant cubed to both sides. I'm going to add this over. So on the left-hand side, I'll have the integral of secant cubed plus the integral of secant cubed. That's 2 times the integral of secant cubed equals secant x tangent x plus ln secant x plus tangent x. And at this stage, I should write my plus c because there are no integrals on the right-hand side. Now divide by 2. I'll write that as 1/2 times and that's it. So these are looping integrals, and they're a little bit tricky. To make life easier on yourself, I recommend, after you get to a place where your integral shows back up, go ahead and summarize your work so far. Say your original is equal to whatever your last line was. So I started with integral secant cubed, I did all this shit. So the integral of secant cubed is equal to this. So I just write that in one line. And then I realize, oh, the thing I want is equal to some bullshit minus the thing I want. So if I add this over, I'll have 2 times the thing I want is equal to some bullshit. So just divide by 2. The problems in your homework are going to have some different constants. I'm doing kind of the simplest version of each of these. If this was integral secant cubed equals some bullshit minus 3 copies of the integral of secant cubed, then I would add all 3 of these over, and I would have 4 times the integral of secant cubed equals this bullshit. So getting to this line where you've got the thing you want equals some known stuff minus some constant times the thing you want, from there you're in good shape. Just add all the copies of the integral from the right back over to the left, and then divide by whatever constant you get there. Questions on this guy? Let's be specific. Questions on any of the actual like algebra or specific steps, like how did we go from this step to this step? Let's focus on those first. Let's make sure our notes are correct.
Question. So I don't know if I'm really understanding where you got the secant squared. I mean, cubed. Right there we have, no, down, more down, more down.
Here?
Down, 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 more. There, on the other side of the equals.
Oh. Remember what we're doing. So this whole thing started with integral of secant cubed equals, right?
Right.
This is the deal with organizing your work nicely and following the sort of rules that I've said about changing bounds and whatnot. Any of one of these lines is equal to the original problem. That's why I'm writing all these equals out front.
I see
So,
now. I see.
yeah, so integral secant cubed equals this shit. So then when I go to summarize, I say, okay, my original problem is equal to whatever my last line was. So original problem and then my last line.
Beautiful. Thank you.
Of course. Other questions, technical questions, like how did we go from here to here? Where did this come from? Okay, then we're just about out of time. So I want to give you one last bit of parting advice here. I told this to my previous class and I want to tell it to you also. Good mathematical writing follows 3 rules. And it's a hierarchy. They matter like in order of importance. First, be correct. Whatever you're writing down, double, triple, quadruple check it to make sure it's correct. First, be correct. Second, be clear. Make sure how you're writing things and the way you're phrasing things and the way you're drawing things, someone who's reading it can tell what the fuck you're thinking. So be correct first, then worry about being clear. And then and only then should you worry about brevity, being brief. So be correct, be clear, be brief, in that order. Brevity don't really matter that much. Correctness and clarity matter a lot more. In other words, don't be afraid to waste paper. Use paper, take up space, write things neatly. Write them big enough that you can see what's going on. Write them clearly and correctly. Then worry about, being clever or brief. That stuff doesn't matter so much. What really matters is that what you're doing is correct and legible and understandable. Then you can start worrying about, once you get to a place where your stuff is clear and correct, and you know that for sure, and you're not stressed about the correctness or the clarity, then you can start worrying about time saving and space saving tricks. Those do exist. There's lots of them, and I'm happy to show you lots. But by far the most important thing is that you're correct. So move slowly. Don't try to go fast. Double and triple check every single step, because you see these problems, they get long. And if you make a mistake on line 2, then line 10 is going to be wrong, and you're not going to know until you go to check your answer. That's frustrating. So take your time. Make sure everything you're doing is correct. Make sure it's well organized. Make sure it's clear. And then we can start learning about space and time saving tricks. But don't stress about that for now. All right? Burn all the trees. Fuck the trees. The math is more important. I love trees. The recycled paper, all that, great. But don't be afraid of using lots of space. And take your time. Okay, these problems aren't that bad. I have an office hour this afternoon from 2 to 3. If you want to come by and solve some more problems, I'd be happy to do that. Like if you want to see why the integral of secant comes out to this, we can do that. If you want to see any other problems from the homework, we can do those too. But for now, I'm going to have to go ahead and end this meeting because our class time is over. So over this weekend, please make sure you're working hard on the homework. Homework 3. It's not terribly long, it's not terribly hard, but there are plenty of things like this where you need to be careful. There's 2 looping integrals. Number 9 and number 14 both loop. Not 14, sorry, number 9 and number 13 both loop. Number 13, this is the one where you need that trig identity. So if I said that was number 14 earlier, I apologize. Yeah, you need this, sorry, not on 14, 13. Okay, so on number 13 here, you're going to substitute for cos t. You're going to let u or x or some other variable be cos t. And in order to make that substitution go through, you first need to replace the sine 2t by 2 sine t cos t. Right? So use this identity on this problem, then make a substitution. And after your substitution, this is going to turn into an integral like the one we just did, like the e to the x cos x integral. 13 and 9 are both looping problems. Do 9 first. The constants that are different here are going to make this problem a little bit trickier than the example we did. But it's totally manageable, and the version of number 9 I put in here has a bunch of different steps. So it'll walk you through the problem. And then when you get to number 13, you'll be on your own. You need to make a substitution first, and it is a definite integral, so you need to be wary of that also. But the looping procedure is exactly as I've outlined it in these two problems. So work hard on these. If you have trouble with any of them, don't hesitate to send me a Canvas message or to request an extra office hour. Remember, office hours are not just at the times that I have listed there, they're also by appointment. I don't think anybody from this section has requested a separate office hour, but I'm happy to do as many as 10 a week. So just if you want some extra time solving problems, one-on-one, whatever, just send me a Canvas message saying so, and we will schedule something. Another option is to snap a photo of your work with your phone and send it to me. I'll be happy to take a look at it and be like, oh, the mistake is on line 3, or instead of x, you need x squared, or whatever, stuff like that. So work hard, don't hesitate to ask for help. Keep everything nice and organized, and review your trig identities, because next week we are going full hog, all trigonometry. So that is it for today. I hope you guys have a lovely weekend, and I will see you either in office hours or on Monday.